Good morning and most welcome to Café Tintin or Tintin Cafe. It's a very cozy environment, mid-central of Gothenburg. It has luxurious plants and we had heavy snowfall this morning. And the pavement's been paved. And as you can see, the light is glittering. Maybe you can see that in the left corner. Here. This glittering doesn't exist when I look at it. It is because of the 50 per second change of current in active current, AC. And this is going to be important, so it could be a good idea to remember. Let's zoom out. I will just mention the name of the article. Recurrent quantum neural network and its application. Authors Laxmidhar, Behera, Indrani and Avshalom, Elitzur. Kalle here will have a little presentation of one of the authors. Let me just get it off. I recommend that you just hold it.
I have a better idea. Let me, if I may, I have a better idea. I think it's good since the names are a little bit unfamiliar to us. They are not the usual English names. I will show you I will show them their home pages with their names.
Very good.
So this is Laxmidhar Behera, and he, as you see, he's a Bonham and Prabhukwel Chair Professor, Department of Electronic Engineering, Indian Institute of Technology, Kanpur, area of specialization, robotics and artificial intelligence. So this is Laxmidhar Behera. Now I'll go to the second author. It's a lady, as you see, Indrani, Associate Professor, Department of Electronics and Electrical Engineering, Indian Institute of Technology. And then the third author is Avshalom Elitzur. He has the same name as the King David's sons, Avshalom. He had a tragic end. He had a very long hair and he died when he rode on his horse and his hair gets stuck in the branches of the tree.
Oh no.
Anyhow, Avshalom Elitzur, he was born in Iran. Let me see. In Kerman in Iran to a Jewish family. I will not read all his Israeli physicist and philosopher. Let us see his specialization. In 2010 he won a Noetic Medal of Consciousness and Brain Research for his contributions to cosmology of mind and quantum theory. Interesting. Let's see his latest publications. What is his latest? It is on Wikipedia page. He mentions publications from 2005 and 2009. In 1987 he published his book Into the Holy of Holies, Psychoanalytic Insights into the Bible and Judaism. Interesting. So I will hand this back to Hans. So you will get to the subject.
Yes, please. Thank you very much, Kalle, for that presentation. He had trouble finding the article, and there is a good reason for this, because this is extraordinary, special, and absolutely new as well. And that this could be, and do remember I use the word could, it could be a way into understanding, connection with our perception, as we mentioned earlier, proprioception, as we spoke about Rosen and proprioception of singular photons. This is a connection to our senses. And this time it's the saccades. Saccades are a bit like H hat, singular events that are distinct. And this realization questions the idea of a linearity of vision. We usually see vision as continuous and instantaneous, that it happens at once. When I got to this coffee shop, Tintin, that I instantaneously got a grasp of the interior and that it was linear. So every inch of the interior that I perceived had the same distance. We know that not to be the case. Instead, singular events in the eyes called saccades are what's happening, and they are much closer to distinct particles. They make distinct stops and they construct a movement. This movement is vision. So vision is a movement. When I read this, it became clearer how vision is primarily located as concept in the movement center of the brain. The motor cortex, and vision has very little connection to the idea of images, colors, and those things. There are not pictures out there, or neither are the pictures in the mind. Blind people also have these saccades, although their images are slightly different, they still have them. I began with the article now. See if I'm spot on here. Recurrent quantum neural network and its applications. This is from a book called The Emergent Physics of Consciousness from Springer. This chapter sidesteps the whole question of whether quantum activity exists in the brain. And goes straight to discussing the need for some sort of quantum effect to explain some of the things that the brain is able to do, particularly the saccade movements of the eyes. The model proposed here suggests that there is a quantum process that affects the average behavior of a neural lattice. The authors remind us that some of the tasks humans perform with ease such as more difficult forms of pattern recognition, are still beyond the capacity of supercomputers. The authors look for a quantum mechanical explanation of the abilities of organisms in this respect. And the chapter discusses human eye movement from this respect. Simulations of brains produce some interesting insights in this respect. When the eye tracks a target, a related wave packet moves not in a continuous classical manner, but in a discrete quantum manner. Which is considered similar to the jumps and rests involved in saccadic eye movement. Eye movements relative to static scenes are not continuous, but involve discrete jumps. If the information is new or difficult to interpret, there are more erratic pauses and even a process of flip back and forth between different images. This again is similar to the movement of quantum wave packets in simulations. Eye tracking experiments show that small eye movements contain errors which are corrected by saccades that bring the eye back to the required position. After 1 or 2 quick saccades, the eye usually becomes adjusted to the target. Saccadic and smooth movements are seen to combine to keep track of the visual target. So already we got into that vision is quantum mechanical. It's not linear. It is happening in jumps, and it's not sucking up an exterior, so to speak, or acting like a camera. Oddly enough, it's as far from a camera, a video camera, or receiver as you can think of. It is at every instant a collapse of a superposition. The author suggests a view of neural information processing where quantum processing affects a neural lattice with spatial structure, also very important. This is known as a recurrent quantum neural network model, or RQNN. This is distinct from other models. I have to add there, this is as different as any other thing could be. Does not really get any more different. This quantum-based model is said to be very successful in explaining the actual nature of eye movements, and, very importantly, to be 1,000 times more accurate than conventional models. So it's not a small difference. I'm commenting a lot here, but it's very dense in the beginning. But I have to add, I've been aware of that the conventional models had been unsatisfactory, to say the least, until this. They have not covered what vision is, and vision as image or color or shape is as far as you can come from vision. And I have to compare with the fall of classical mechanics. This is similar. We've been very persistent in the old model, which is intuitively very, very heartful and emotional, but still not correct. We do not see things. There are no things out there to be seen. I'll try to keep my comments low. I continue. The authors hope that their work will encourage researchers to study the brain from a quantum perspective. Microtubules are mentioned as the most plausible location for quantum activity in the brain. With electrons inside hydrophobic pockets localized towards either to the A or B end of the tubulin dimer. And capable of being in a superposition of these states. Apart from this, the authors simply describe their model as idealized. And decide to remain silent on the question of the actual physical structure of quantum information processing. Or the problem of decoherence. Now I go into the technical part. I will take it slowly and pause often. But do note, as the authors said initially, the technical part almost parallel to the part as treated earlier by Stuart Hameroff and Roger Penrose, will not be covered. It is vision alone, or the movement that is what we call vision. Summary. Although the biological body consists of many individual parts or agents, our experience is holistic. We suggest that collective response behavior is a key feature in intelligence. A nonlinear Schrödinger wave equation is used to model collective response behavior. It is shown that such a paradigm can naturally make a model more intelligent. This aspect has been demonstrated through an application. Intelligent filtering, where complex signals are denoised without any a priori knowledge about either signal or noise. And this is, of course, very close to the voice of the friend. We do not have to know what it says, where it's from, or even how it sounds. Such a paradigm has also helped us to model eye-tracking behavior. Experimental observations such as saccadic and smooth pursuit eye movement behavior have been successfully predicted by this model. Nine-one intelligence still ill understood Natural intelligence is what determines a normal thought process of a human. Artificial intelligence is a property of a machine that gives it the ability to mimic the human thought process. The foundational framework for intelligent computing lies in our proper understanding of mental processes. Though the term intelligence is still not completely defined, research in artificial intelligence has focused on 5 components of intelligence. An intelligent system should have the abilities to understand, perceive, reason, solve problems, and moreover, learn from past experiences. The understanding of cognitive processes consists of the formulation and solution of the 3 fundamental problems in the design of intelligent machines. That intelligently observe, predict, and interact with their surroundings. These problems are known as 1. The system identification problem. 2. The stochastic filtering problem. And 3, the adaptive control problem. Here we address the issue of the intelligent stochastic filtering problem. The main question, therefore, is: can we design a method that allows us to estimate any signal embedded in noise without, and this is important, without assuming any knowledge about the signal or noise behavior? Information processing in the brain is mediated by the dynamics of large, highly interconnected neural populations. The activity patterns exhibited by the brain are extremely rich. They include stochastic, weakly correlated local firing, synchronized oscillations and bursts, and propagating waves of activity. Perception, emotion, etc. are supposed to be emergent properties of such complex nonlinear neural circuits. Different architectures of interconnected neurons, such as feed-forward and recurrent neural networks, have been explored to study global brain behavior. Instead of considering one of these conventional neural architectures, an alternative neural architecture is proposed here for neural computing, namely a recurrent quantum neural network. The acronym is RQNN, and I suggest you memorize it because this will become more current. This term entails that the individual neural response does not play a significant role when the collective behavior of a neural lattice is observed. Population dynamics studies of bird flocks and fish schools show that individual dynamics does not play a role in group dynamics. Once more, a comment from my side. This is pretty recent. We did not have any understanding for a flock of starlings before. And for everyone who's seen starlings flocking, I think you pretty much understand that it cannot be coordinated by individual responses from each starling. How does it work? This extraordinary beauty of their movement. End of my comment. Hence, ignoring individual neuron dynamics while considering average lattice behavior is sometimes a sound methodology. The proposed RQNN is quite different in spirit and objective from the QNN architecture available in literature. As these QNNs synthesizes a neural lattice using individual neural responses. The collective response model proposed in this chapter entails that there exists a quantum process that mediates the average behavior of a neural lattice. This collective response is described here using Schrödinger wave equation. We show that the closed loop RQNN dynamics exhibits a soliton property. We exploit this property for stochastic filtering. The signal estimation is shown to be quite accurate. Moreover, filtering using this approach is done without any a priori knowledge of either signal or noise. Intelligent filtering, denoising of complex signals. According to Bassi, every solution to a stochastic filtering problem involves the computation of the time-varying probability density function. on the state space of the observed system Dave's proposed a novel model, a parametric avalanche stochastic filter. Using this very concept, his work is the main impetus for the present work, which we hope will motivate others to explore this new approach. Check it.
50 minutes.
Okay, 10 more. For stochastic filtering applications, we make the hypothesis that the average behavior of a neural lattice that estimates a stochastic signal is a probability density function that is mediated by a quantum process. We use the Schrödinger wave equation to track this PDF function, since it is a known fact that the square of the modulus of the psi function the solution of this wave function is also a PDF function. It will be explained in detail later in this chapter that the Schrödinger wave equation becomes nonlinear when its potential field is excited by a feedback signal that is a function of psi. The state of the quantum process. It is known that the nonlinear Schrödinger wave equation exhibits a soliton property which is necessary to track non-dispersing wave packets. Representative of the time-varying PDF This is a generic identity of a stochastic signal under observation. I will try to make a summary so far. Excuse me the very density of the article. And when I say density, I refer both to the novelty of what is proposed. It is meaning that to see something or hear something, we do not identify things. There is no word identification. There are no singular things to identify. And it's also indicating that perception is not individualistic. I am not perceiving. The stochastic saccadic movements, it's what corresponds to perception. And it's not happening within me. It's not happening without me, outside of me. This is the Schrödinger quantum wave equation. It does not take an origin, and it does not identify certain things for its understanding. Once more, it's very helpful here to think of the voice of the friend. I have returned to it many times, and here it's even more helpful. For to understand the voice of the friend, we cannot, and I repeat, cannot identify from who it is, what words are said, in which rhythm, melody, pitch they come. And it is not externally situated. Voices do not appear externally, exogenous, mysteriously. This is the first time the quantum wave equation enters into perception in a very decisive manner. And the success in also explaining eye movements, which until this has remained unexplained or provenly falsely explained. The eye movements with the saccadic movements making tiny quantum jumps. Jumps that do not depict an outside and does not receive an image of an outside. Vision is not vision. It's not images. There are no pictures to perceive. colors, shapes. This is as far as you can come from James Locke's version of two aspects of perception. One aspect of things outside, having length, width, breadth, mass, and situatedness, locality. That is wrong. The second aspect of Locke, that the subject to this first aspect adds color, surface structure, depth, and so forth, is also wrong. And the underlying assumption, never mentioned by anyone, Locke nor Hume, nor any modern scientist of cognition, that there is a pre-existing world, is also false. The concept of an outside world simply does not make any sense. It's non-computable, and it is as a big of an illusion as the extra worlds of, for instance, Hugh Everett. As an added bonus for me, you've seen flocks of starlings, schools of birds, by the thousands, moving like one hand beautifully, going into itself, rounding each of the tenth of thousands of birds, simultaneously coordinated, now gets its explanation. It is not coming from solitary perception in each bird. Perception in itself is not individualistic. It's not so long ago it was proven individualistic perception would never work with a starling flock exceeding 10 birds, much less so for 100, and even less, of course, for flocks with thousands and thousands of birds. Maybe we have a little comment here. I'm going to give the microphone to my dear colleague here. Oops. It's a new device, so be careful. Hooks on a bit different.
Let me see if I understand correctly. No, I don't understand this. Oh, okay. Okay. Hello. So thank you for this paper by these three scholars, Avshalom, Elitzur, and Indrani and Laxmidhar Behera. I was thinking about the paper that we went through some 3 weeks ago. There was a female professor, and it was about projection. So the eyes don't see, they see, but they project first. They project. You don't have an objective word. In that paper, you had an image of a fisher, a fisherman. Thank you, fisherman, and. Perhaps you can put a link there when you find out. Okay, anyhow, so there was The vision was like a projection, and so it's good to compare the Schrödinger wave to the eye. And visually, we also have like the eyebrow. Okay, it's a banal comparison, but it's the eye. We don't have an objective world out there, but there was one phrase that I would like to criticize in this paper. And this paper, it's a little bit confusing. It has two titles really: Recurrent Quantum Neural Network and its Applications. And the second title is a recurrent quantum neural network model to describe eye tracking of moving targets. That was the second title. I don't even know which is the right title, but anyhow. So the phrase is on page 2 in my edition. This wave packet moves like a particle. This wave packet moves like a particle. So in my understanding, we see our things like a wave, like this. Okay, so far so good. And then we see something. There's a collapse of the superposition, and then we have a particle, like in the dichotomy, if we call it dichotomy between wave and particle. But they say that the wave packet moves like a particle. I think it's confusing because the wave moves like a wave. It cannot move like a particle because particle is like this linearity. So I don't like this. This phrase is not the best, but I know what they mean probably, and they don't mean like yes. And I also like your comparison with Derrida's The Voice of the Friend, and like so Derrida's point was is that when we hear somebody, I hear you. Okay, this is. It's not the voice itself, your origin, that is important, but the voice itself that we should interpret. When we have a wave doesn't have a origin that's important. So it is a way of going away from the particle or the origin thinking. So the way to the solution to understand reality is the wave. To make a banal pun. Let me now return to you and see if you have something to add to my comment.
Try to adjust this rather cumbersome microphone here. Yes, very good. Of course, there is no particle until the collapse of the potentiality. Then you have a particle, and for convenience it's better to stick to that clear distinction, otherwise understanding will be confused. But often it's the case that they confuse that. They speak about particle wave or probability for a particle, which is also, oddly enough, a wave. So there are many sinkholes to step one foot into. There are loads of problems that these authors are solving by introducing the Schrödinger wave equation. You will be surprised how many unresolved mysteries there are within the science of cognition that we actually are aware of. This is extraordinary to read, and we have a situation that is not very dissimilar from the one haunting, so to speak, a specter of physics at the late 19th century and beginning of 20th century, when paradoxes became too demanding, too frequent to be ignored anymore. The flock of starlings is one of my favorite examples. I suggest you all to have a look at a starling flock and see the amazing patterns they are doing, and the coordination is beyond belief. The authors of the paper literally say it is beyond belief. It is not possible within the ordinary reality. This is the Schrödinger wave equation doing its work. Put a little pause there, maybe. The proposed model is an improvement over the model proposed by Daves in two respects. First, the movement of wave packets as solitons and non-linearly modulated spatial potential field. We also noted that it is very difficult to heuristically tune the parameters of the nonlinear Schrödinger wave equation while tracking the probability density function. This led us to make use of the evolutionary computation approach based on the univariate marginal distribution algorithm to identify these parameters in known cases of signals embedded in noise. In a recent work, we have shown that both Gaussian and non-Gaussian PDFs are learned by the proposed recurrent quantum neural network. And the signal estimation is quite accurate in the presence of a noise level up to 6 decibels. The results were also compared with the classical filtering algorithm. In this work, we consider the stochastic filtering of non-stationary signals, including the speech signals. The speech enhancement capability of the proposed RQNN is also established in real time. Thus, this chapter provides a complete framework for learning a stochastic signal in terms of its probability density function. The other important feature of our proposed model is the novelty of its application to signal processing. The popular Kalman filter assumes that the dynamic process is linear with Gaussian observation noise, and the algorithm is too computationally intensive for a system of practical complexity. The other important feature of our proposed model is the novelty of its application to signal processing. The popular Kalman filter assumes that the dynamic process is linear with Gaussian observation noise, and the algorithm is too computationally intensive for a system of practical complexity. The other important feature of our proposed model is the novelty of its application to signal processing. The popular Kalman filter assumes that the dynamic process is linear with Gaussian observation noise, and the algorithm is too computationally intensive for a system of practical complexity. The extended version, popularly known as EKF, makes many approximations to include nonlinear processes as well. However, in practical situations, the stochastic noise cannot be limited to a Gaussian or even a unimodal distribution. In contrast, the proposed RQNN estimates a signal without any a priori assumption on the shape and nature of the signal and the noise. In a nutshell, we propose a stochastic filtering scheme that is a step forward towards intelligent filtering. (921) RQN architecture used for stochastic filtering. The architecture of the RQNN for filtering a one-dimensional signal embedded in noise is shown in figure 9.2. The signal YT is the actual signal YAT. The depictions can be found in the following links. And we go into an explanation of the quantum model of intelligent behavior. That chapter is 9.3, a comprehensive quantum model of intelligent behavior. Biological organisms perform many complex tasks with ease. Although we may have supercomputers that have reached the level of computing power beyond our imagination, some of the tasks we perform, such as pattern recognition and language understanding, are still beyond the reach of such supercomputers. Can quantum mechanical models better account for such complex behavior in biological organisms? The rest of this chapter is devoted to this question. We propose a theoretical quantum brain model to explain human eye movement behavior. Where the same collective response attribute of natural intelligence plays the key role. Where the same collective response attribute of natural intelligence plays the key role. And I would say that might be the most important sentence in this second part of the lecture. Intelligence and the saccades are closely linked. Vision is understanding itself, whether it be endogenous or exogenous. While simulating the quantum brain model, two very interesting phenomena are observed. First, as eye sensor data is processed in a classical brain, a wave packet is triggered in the quantum brain. This wave packet moves like a particle. Secondly, when the eye tracks a fixed target, this wave packet moves not in a continuous, but rather in a discrete mode. This result reminds one of the saccadic movements of the eye, consisting of jumps and rests. However, such a saccadic movement is intertwined with smooth pursuit movements when the eye has to track a dynamic trajectory. In this sense, the proposed quantum brain concept is very successful in explaining the nature of eye movements that also accord with experimental observations. Very important. This is possibly the first time this is made. Nine 4. The RQNN-based eye tracking model. There are certain aspects of brain functions that still appear to have no satisfactory explanation. As an alternative, researchers are investigating whether the brain can demonstrate quantum mechanical behavior. According to a current hypothesis, microtubules, the basic components of neural cytoskeleton, are very likely to possess quantum mechanical properties due to their size and structure. The tubulin protein, which is the structural block of microtubules, has the ability to flip from one conformation to another as a result of a shift in the electron density localization from one resonance orbital to another. These two conformations act as two basis states of the system according to whether the electrons inside the tubulin hydrophobic pocket are localized closer to alpha or beta tubulin. Moreover, the system can lie in a superposition of these two basis states, that is, being in both states simultaneously. That is, being in both states simultaneously. Which can give a plausible mechanism for creating a coherent state in the brain. Penrose therefore argued that the human brain must utilize quantum mechanical effects when demonstrating problem-solving feats that cannot be explained algorithmically. In this chapter, instead of going into the biological details of the brain, we propose a theoretical quantum brain model using the RQNN. The RQNN model proposed in section 921 has been modified a little to cope with the present application. Instead of using a linear neural circuit to set up the potential field in which the quantum brain is dynamically excited, instead of using a linear neural circuit to set up the potential field in which the quantum brain is dynamically excited, the present model uses a nonlinear neural circuit. This fundamental change in the architecture has yielded two novel features. The wave packets fx.t equals psi x.t to the potential of 2 are moving like particles. Here, psi xt is the solution of the nonlinear Schrödinger wave equation that describes the proposed quantum brain model to explain eye movements for tracking moving targets. The other very interesting observation is that the movements of the wave packets while tracking a fixed target are not continuous but discrete. These observations accord with a well-known saccadic movement of the eye. In a way, our model is the first of its kind to explain the nature of eye movements in static scenes that consists of jumps, saccades, and rests, fixations. We expect this result to inspire other researchers to further investigate the possible quantum dynamics of the brain. And this last is extraordinarily important. Moves and rests. Now we see waves and particle as what they do. A particle rests, a wave moves. And in between them, there is a jump, going from one to the other, not a linearity of smoothness, but rather a quantum leap from one state to another without intermediate possibilities of stops. I will make a conclusion here, but I will also read the concluding remarks by the authors. And now we skip to page 347. It's time to put it in order. Page 347. 9.5 Concluding Remarks. We presented an alternative neural information processing architecture where a quantum process mediates the collective response of the neural lattice having spatial structure. The key feature of this model is collective response behavior that is identified as an attribute of intelligent behavior. The proposed RQNN is governed by a single dimensional nonlinear Schrödinger wave equation. The proposed RQNN is governed by a single dimensional nonlinear Schrödinger equation. Very important. I think it's easy to see here now that the old model is slowly dissolving into its foundations in the quantum wave equation, where situatedness and particleness, if you like, are derived features of reality. Where perceiver and perceived is not disjunct in time nor in space. You can see here how entanglement, the directness of perception, without any delay, is what regulates reality and our perception of it. It is a oneness, and the single wave is very important to remember here. Now you can see the wholeness. You can see how the Klein bottle is constantly interpenetrating itself, and how the self is the nexus, the hub of reality, not something standing apart as in the classical model. And how what is explicit and implicit go hand in hand. What is hidden, what is out in the open, is what together makes up reality, not either or. In the classical model, what is implicit is simply absent or empty, blank or dark, not there. It is the horror vacui that the classical model paradoxically constructs. And now we also see the persistent turn towards the light in the classical Newtonian paradigm, where put into the clearness of the fluorescent light is the only thing that can produce knowledge, and where a persistent change of pace is not possible. There is no acceleration, there are no jumps. It's a homogeneous, linear, non-understanding. The linearity itself is not of this world. It is only the blankness that we call linearity. And distance understood in this way this is an opening to an encompassing present understanding, where becoming is not obfuscated, where clearness is what is happening in between, not in either spot, and where polarity is the only way of trying desperately to grasp for understanding. Well, as the song says, I think I better leave now. I say thank you very much for this first rather deep dive into RQNN. And I say thank you to the authors Laxmidhar, Behera, Indrani and Avshalom Elitzur. I think this is an extraordinary, important step in a direction that leads to an understanding that is broader, more foundational, and doesn't take polarity as its starting point. This paper has proven to be very hard to find as a downloadable copy, but I will make my very best to find it on the net, to give links in the description beneath. All welcomes are most welcome for this rather new subject. It's been a rather compacted week with a lot of things to do, but I think this is a good end of this week's lecture series, and I will come back with a summary of the RQNN and try to compare it, to parallel it to other texts. That usually is very helpful to approach it from another side. It leads to the same quantum wave understanding that perception itself takes. Thank you very much and have a very pleasant afternoon. Bye bye. Yeah. We end with a snowy picture of Gothenburg. This 3rd of February. Bye bye.